Hi, my name is Prasoon, and I'm going to present my paper titled Can LLMs Replace Neil deGrasse Tyson Evaluating the Reliability of Large Language Models as Science Communicators? This paper was accepted in the main track of EMLP 2024, and let's start. So, before discussing the main ideas of this paper, we need to solidify what we actually mean by scientific communication. So, scientific communication is the practice of conveying scientific information such that it is understandable by general public, not necessarily by people who are subject experts in the field. But to assess the quality of scientific communication, you need to ensure that the large language models are stress tested to their utmost limits. So the motivation of this study arises from the fact that large language model based AI chatbots are prevalent everywhere in the industry. And we know the innate risks of using large language models, such as temporal degradation of facts and the most popular term of them all, the hallucination, which refers to the scenario when the text which is produced by large language models is not faithful to a given source input. And we have seen papers in which large language models have been shown to miss out on small details, especially in the domain of science. And through this study, we want to benchmark all open source as well as proprietary models on their capabilities of doing scientific miscommunication. So the research questions that we are targeting in this study are: can existing large language models answer scientific reasoning questions successfully and faithfully, which require nuances of scientific knowledge? Are language models effective at abstaining from assertively answering scientific open problems? So we know that there are a lot of problems in science which are considered to be open, and there does not exist an answer to these problems. So we want to see if the language models know if they do not know the answer to this problem, and are they abstaining from answering these problems at all? The third research question that we are targeting is: can large language models successfully verify their own responses? And the fourth research question that we target is: can human evaluators be misled by incorrect yet confident large language responses in the domain of scientific knowledge? So, a major contribution of this study is the development of the dataset which we call SCIPS QA. It is a collection of 742 problems which are grounded in extremely complex scientific ideas. The problems are in Boolean format, and the dataset is comprising both closed problems, the problems for which there exists an answer in the scientific literature, as well as open problems, the problems for which there does not exist an answer. And the questions are synthetically generated from GPT-4 Turbo, and all the questions have been sourced from openly available research blogs and Wikipedia articles which are present on the internet. And on the right side, you can see a snippet of some of the questions which are present in SCIPS QA across three subjects: physics, chemistry, and maths. So, particularly in chemistry, you can see the question. There is a particular chiral compound which is being shown in the question, and the responses which are present in the white rectangle are the responses which are generated by GPT-4 Turbo. And you can clearly see that this response is not correct, as is evident from the correct reasoning which is given below. On the top of this figure, you can see a more detailed granular composition of SCIPS QA. It has 500 closed problems and 242 open problems. And the toughness of the SCIPS QA is shown on this slide, where we have collected 40 random problems from the popular scientific benchmarks such as MMU and SciQ, and we have shown that models as developed as GPT-4 Turbo perform worst on SCIPS QA, and it overall represents a longer horizon for improvement of scope of models in SCIPS QA. This is a subject-wise decomposition of problems in SCIPS QA, the topics that are concerning some problems. So what all experiments are we doing? So first of all, we are benchmarking 13 open source and 3 proprietary models. The open source models are from the family Llama 2, Llama 3, Mistral, and the proprietary models are from the GPT series. And we are testing their performance at SCIPS QA. Apart from testing their performance, we are also collecting reasonings associated with the questions from proprietary models, and we are checking for the amount of hallucination or unfaithfulness which is present in these reasonings using a low resource internal hallucination metrics called Subject GPT. We are evaluating the reasoning passages across many dimensions such as convincingness and factuality using large language models as evaluators themselves. And we are also performing human evaluations. So we'll give a detail of these. So first of all, we are collecting 2 types of responses, which we are calling main response collected at temperature 0, and 10 stochastic responses, which are collected at temperature 1. From proprietary models, we not only accept responses such as yes, no, or I do not know, but we also accept responses containing the reasoning passages of the questions. But from the open source models, we are only collecting responses yes, no, or I do not know. And this is the overall result of the benchmark on the 13 open source models as well as the 3 proprietary models. There are various type of metrics that we have designed, such as the main response accuracy, which judges the accuracy from the main response. There is stochastic response accuracy, which is the MSAC, which takes a measure of the answers present and it judges the correctness based on that. And there are separate metrics for closed questions as well as open questions. So you can see that, and there is also variability in the stochastic responses. There are multiple stochastic responses which are sampled at temperature 1. So we are trying to see if the LLMs are consistent in answering, and we can see that the GPT models are fairly consistent in not changing their responses across sampling at temperature 1, but models such as Llama 2 are fairly inconsistent. And one of the main highlights of this evaluation benchmark was that Llama 370 billion stood out as one of the leading models for closed questions as well as open source questions. For open source, we found that for the open problems, we found that the non-instruction fine-tuned version gave the best results, and for the closed questions, we found that 70 billion instruct gave really good results. And for the quantification of hallucination, as I said, we are using self-check GPT, and we are using various variants of self-check GPT, such as BERT score and natural language inference. And all these methods basically allot a sentence of the main response, a score of 0 to 1, depending if it's not hallucinated or fully hallucinated at all. And we found using statistical significance results that GPT 3.5 Turbo and GPT 4 Turbo were fairly indistinguishable from their capability of producing hallucination text, but Texta, which is recently produced, really different results as compared to these two models on the basis of the metric which was provided by self-check GPT tests. And then we also evaluated using responses of large language models across following attributes: convincingness, factuality, and information mismatch. So, convincingness, as the name suggests, describes the persuasiveness of the reasoning responses which were given by large language models. And all these dimensions were tested using large language models as evaluators themselves. So, we used GPT 3.5 Turbo and GPT 4 Turbo as the verifiers. And given a reasoning response, we gave them a score in the range of 1 to 5 for all of the 3 dimensions: convincingness, factuality, information mismatch. These are the prompts that we used. The source, as you can see for the information mismatch, I would like to point out that the source document was the main response and the generated text was the stochastic responses. And that's how we are trying to evaluate the amount of similarity between the main responses and the stochastic responses using large language models as verifiers. And we found quite interesting results that we found that these verifiers are not able to distinguish between correct and incorrect responses. Almost similar distribution of the convincing factor score and factuality scores were given for both the correct as well as incorrect. So it was an alarming result that they cannot verify their own responses. And when we repeat this same setting of experiment for humans, we found a similar result. And humans were also not able. So we employed so for each subject, physics, chemistry, maths, and theoretical computer science, we employed 2 graduate level students for testing the answers, and we found similar results as we found when using large language models as verifiers. We found that human evaluators were not able to distinguish between correct and incorrect responses across the dimension of convincingness. So they found incorrect answers as convincing as the correct answers, and this was really alarming. So these are some of the findings that have been summarized by me. So we find that while proprietary models such as GPT-4 Turbo are generally better, open source models such as particularly Llama 370 billion models are fairly good at answering closed problems in SkipsQA. And all the experimental large language models are far from understanding the nuances of scientific rigor. And we found various aspects, various shortcomings of large language models in being used as verifiers of the information which is generated by them, especially across dimensions such as persuasiveness and factuality, etc. And the persuasive style of GPT-4 Turbo was enough to deceive humans. And the biggest contribution of this study was the creation of SkipsQA, 742 complex Boolean scientific problems requiring deep knowledge and deep knowledge retrieval and extensive reasoning to answer. We benchmarked 13 open source models and 3 proprietary models on SkipsQA, and we investigated large language models' capability to verify their own responses together with performing human evaluation results. So overall, this study proved that large language models are nowhere close to being good at scientific communication, and we need rigorous research work in that direction. Thank you.